Hi, I'm Mark Caholen from AMETEK Brookfield. In this training module, we will look at all the available accessories used with standard viscometers and rheometers that can extend the capabilities of the instrument when just using standard spindles. We'll also look at yield stress measurement technique. You may have a need to locate the instrument in such a way that the standard spindle length will not allow for complete immersion of the spindle. In cases like this, possibly mounting the instrument above an environmental chamber, for example, you will have to extend the spindle through the top of the chamber and into the container inside. This can be accomplished in two ways, either using the Type D spindle extension link with two hook couplings or using the Type S spindle with one hook coupling. Another accessory that simplifies installation and removal of threaded coupling spindles is the Quick Connect coupling. Once installed on the instrument and spindle, you simply lift up the sleeve that exposes the coupling on the instrument. Align the spindle coupling to the instrument coupling and lower the sleeve to lock the spindle in place. The latest design for connecting the spindle to the instrument is the magnetic coupling. It is by far the fastest and safest way to attach and remove spindles. Spindle installation and removal becomes a one-handed operation. There is no added stress applied to the suspension during this process. The barcode spindles are used for 21 CFR Part 11 compliance when matched to a 21 CFR Part 11 compliant rheometer. This system replaces the obsolete Easy Lock connector. The coaxial spindles and chambers have a defined geometry that support the calculation of shear stress and shear rate. Rather than reporting viscosity as a function of RPM, you can define the viscosity based on shear rate. This is very useful for determining the viscosity of your material at shear rates that correspond to how it is applied. For each spindle, there is a corresponding chamber that must be used for accurate viscosity and shear rate results. Also available is a disposable spindle and chamber for the AMETEK Brookfield small sample adapter and thermocell accessory. All coaxial spindles must be used with the corresponding accessory they were designed for. Each spindle and chamber combination requires a specific sample volume that assures that the spindle is properly immersed in the sample. When using any coaxial geometry accessory, such as the small sample adapter, the UL adapter, thermocell, or DIN adapter, an additional 1% must be added to the instrument accuracy. So test results would now be plus or minus 2% the full scale range rather than 1% when using standard spindles. These accessories all require the use of an alignment bracket, which results in an increase of 1% accuracy. The advantage of using coaxial cylinder geometry is the ability to calculate shear stress and shear rate. Shear stress is reported in units of dynes per square centimeter. As we learned in a past module, each spring range has a full-scale torque value measured in dyne centimeters of force. To calculate shear stress, we take the full-scale dyne centimeter value of the spring being used. By looking at the resistive force being applied to the spring by the fluid, displayed as percent torque, we calculate the actual dyne centimeter force, which is that percent of the full-scale dyne centimeter force. Next, we must determine the area of the spindle that is in contact with the fluid. To do this, we must know the radius and length of the spindle to calculate the area in square centimeters. Since we know the resistive force in dyne centimeters, we can divide the force by the area in square centimeters to determine the stress in dynes per square centimeter. Now let's look at shear rate. In an earlier module, we learned how to calculate shear rate. Here you can see that we need to know the radius of the spindle and chamber and the speed of the spindle in revolutions per minute. This formula calculates the shear rate at the surface of the spindle. Once the shear stress and shear rate are known, we can calculate viscosity. Simply divide the shear stress by the shear rate for viscosity in poise. 1 poise equals 100 centipoise. As the name states, the small sample adapter is designed to measure a small sample volume. If you can't provide 500 mLs of sample for testing, then using this accessory reduces sample size down to 2 to 16 mLs, depending upon the spindle chosen. It uses coaxial spindle and cylinder geometry and can attach to all regular benchtop viscometers except for the cone and plate viscometer. A beneficial feature of the small sample adapter is its ability to equilibrate sample temperature rapidly with the included water jacket used in conjunction with an optional temperature bath. Rather than take several hours for a beaker with sample to equilibrate, the small sample volume allows for rapid, controlled temperature ramp tests. Another advantage of this accessory is the coaxial cylinder geometry, which allows for testing at defined shear rates and measuring shear stress. The UL, or ultra-low adapter, was designed to expand the lower measurement range of AMETEK Brookfield standard viscometers. When used with an LV range instrument, the range is lowered to 1 centipoise at 60 RPM. With the RV range at 100 RPM, the minimum range is 6.4 centipoise. The HB range can also be lowered to 51 centipoise at 100 RPM. It consists of a single spindle with a matching chamber. The sample size is fixed at 16 mLs, and it also attaches to all benchtop viscometers except for the cone plate viscometer. As with the small sample adapter, temperature control is accomplished with the included water jacket. The coaxial cylinder geometry allows for controlled shear rate tests and the ability to record shear stress. The DIN adapter is designed to meet the German Institute of Standardization requirement DIN 50319 for viscometer spindle geometry. It defines the maximum gap allowed between the spindle and the chamber wall. The ratio of the chamber radius to the spindle radius must be less than or equal to 1.1. When using standard spindles in a 600 ml beaker, it's possible that laminar flow does not continue out to the beaker wall because the product itself acts as the wall. This standard assures that there will be laminar flow gradient from the spindle to the chamber wall. As mentioned in an earlier model, a temperature change of several tenths of a degree can affect product viscosity. Therefore, all tests should be performed at a specific temperature based on your needs. To do this, a temperature bath can be used with either a beaker or with any accessory with a water jacket. When using standard spindles, you can immerse a 600 ml low-form beaker into the bath with the guard leg in place. When using any accessory with a water jacket, flow can be directed to the water jacket from the bath. Remember, it is much faster to reach thermal equilibrium with any water jacketed accessory since sample volume is reduced. Ambient conditions could range from 18 to 25 degrees, so it's important to pick one specific temperature when a method is written for ambient temperature. Using distilled water, temperature may vary from 5 degrees centigrade up to 95 degrees centigrade. If your sample requires testing at elevated temperature, the thermocell accessory is perfect for these applications by shielding the container to prevent any exposure to the hot sample. The ASTM D4402 standard test method for asphalt at elevated temperature and the Strategic Highway Research Program, or SHRP, tests require temperatures above 100 degrees centigrade. At these temperatures, high temperature fluid is required in the bath, which creates a burn hazard. The thermocell uses the same coaxial cylinder geometry as the small sample adapter, and the sample size is also minimized. Temperature can be controlled from about 15 degrees centigrade above ambient temperature to a maximum of 300 degrees centigrade. There is one size chamber available for the thermocell, which is the same dimensions as the 13R chamber. So all the coaxial spindles that can be used with the 13R chamber can be used with the thermocell. AMETEK Brookfield offers a disposable version of this chamber for materials that solidify once cooled. Rather than clean a hot chamber, the spindle can be removed and the sample be allowed to cool and solidify. The chamber can then be disposed of. For highly viscous materials, the long extension link connecting the spindle to the instrument can result in some vertical and lateral spindle movement, resulting in unstable readings. To prevent this movement, solid shaft spindles are available. The Helipath stand was designed for use with fluids that have slow flow rates and exhibit channeling. A quick test to determine whether your material is slow flowing is to take a pencil, stick it in the sample, pull it out. If there is a hole left in the sample, then it is slow flowing and will require the use of the Helipath accessory to measure the viscosity of these materials. The instrument head is attached to a drive motor on the upright rod of the stand. A T-bar spindle is attached to the instrument and placed just below the surface of the sample. The instrument is then started at a recommended speed between 5 and 12 RPM. Exceeding 12 RPM will cause the T-bar to pass through a portion of the channel created on the downstroke. Once the instrument is started, the drive motor switch is turned on. The approximate speed of the motor is 1 inch per minute. As the drive motor moves the spindle down through the sample, the helical spindle path overcomes the channeling issue. The T-bar spindles do not have a defined shear rate, but in general, the shear rate is very low. Depending upon the spring range of the instrument being used for testing, the viscosity range is from 800 to 10 million centipoise. The sample size and container shape are flexible, but it's best to have at least 1 inch in depth for the spindle to travel through. The spindle should be no less than 1/4 of an inch away from the container wall. It's best to gather as much data as possible for at least 1 minute, possibly 2, if the depth of the sample is 2 inches. This data can then be averaged for a more representative result. Thick pastes and gels typically tested with the Helipath accessory are peanut butter, yogurt, and cold creams. Sample volume is variable based on the container used for testing. In many cases, the sample is tested in the container it's packaged in. Toothpaste tube ends are cut open, and yogurt containers or peanut butter jars are used. The Helipath stand spindles are known as T-bar spindles. They should not be used to perform an instrument calibration check. Always use the standard spindles when following a calibration procedure. All spindles should be removed from the instrument for cleaning. Extra care must be taken with the T-bar spindles, since the T and shaft are very thin. Here we see typical Helipath data. An HB range DV3 instrument with a TF spindle was used for all tests. 2 tests were performed on each of the 2 samples. Torque data was collected at 20-second intervals with a downstroke time of 4 minutes, followed by an upstroke time of 4 minutes. Sample depth would have been at least 4 inches. As you can see, the blue product is easily distinguishable from the red product. Reproducibility is also very good with these samples. Notice that the downstroke data on both products has a higher torque value than the upstroke data. What has happened is that the channel left during the downstroke contains air, which reports as lower viscosity on the upstroke as the T-bar moves through these air voids. This data is also very consistent from point to point, only varying by several % torque. Some products do not produce as steady a data set, and torque can vary greatly. Therefore, it's important to gather as much data as possible on the downstroke and report the result as an average value. This helps smooth out the results. We recommend using only the downstroke data for data analysis, since this data is gathered from a non-disturbed sample. Vane spindles can accommodate various container sizes. Sample volume will be based on the amount of sample needed to fill a container deep enough for the vane to be fully immersed into the sample. The container diameter should be twice the vane diameter. Vanes can be used with a standard viscometer or an AMETEK Brookfield DV Rheometer. When performing static yield tests, the spindle should be inserted carefully to avoid disturbing the sample. Several rheological properties of a fluid can be determined using a vane spindle. Static yield tests can be performed with a DV Rheometer, and viscosity can be measured with any standard viscometer. Vane spindles are ideal for measuring highly viscous fluids like pastes, creams, gels, and materials with large particles. The last accessory we'll discuss is the spiral adapter. It was designed to measure paste-like samples in smaller volumes. 50 mLs is the typical sample volume. A screw-type spiral spindle pumps the fluid through the annular gap between the spindle and chamber. Shear rate can be varied from 0.07 reciprocal seconds up to 166 reciprocal seconds. The upper viscosity limit is 9 million centipoise. The low range is a function of the fluid's pumpability. Very sticky, stringy materials can be pumped at very low speeds, but other materials require a higher speed to keep them moving through the chamber. Like the other accessories, the accuracy of the chamber is 2% of the full-scale range. Applications include solder paste, screen print inks, and soft putty. Now we'll take a closer look at three types of cone plate instruments, their geometries, operation, and applications. Just as coaxial geometry allows for shear stress measurements and control shear rate testing, cone plate geometry can also measure shear stress and control shear rate. Shear stress is reported in units of dynes per square centimeter. As we learned in a past module, each spring range has a full-scale torque value measured in dynes centimeters of force. To calculate shear stress, we take the full-scale dynes centimeter value of the spring being used, and by looking at the resistive force being applied to the spring by the fluid, displayed as percent torque, we calculate the actual dynes centimeter force, which is that percent of the full-scale dynes centimeter force. Next, we must determine the area of the cone that is in contact with the fluid. To do this, we must know the radius of the cone to calculate the area in square centimeters. Since we know the fluid's resistive force in dynes centimeters, we can divide that force by the area in square centimeters to determine the stress in dynes per square centimeter. Now let's look at shear rate. In an earlier module, we learned how to calculate shear rate. Here you can see that we need to know the cone speed in radians per second and the cone angle in degrees. This formula calculates the shear rate. The cone angle assures even shear throughout the sample. Picture a marching band in a parade. They form one long row from one side of the street to the other. When they must make a left turn onto an intersecting street, the band members on the left simply rotate slightly while stepping in place. The band members further to the right of the line must run quickly to make the turn to keep the line straight. So, with the sample near the center of the cone moving very slowly, and the cone angle increases the distance from the cone to the plate as you move to the outside of the cone. By creating a larger distance between the cone and plate as the radius of the cone increases, its shear rate remains constant. Once the shear stress and shear rate are known, we can calculate viscosity. Simply divide the shear stress by the shear rate for viscosity in poise. 1 poise equals 100 centipoise. So by multiplying by 100, we get centipoise. There are 3 AMETEK Brookfield models that incorporate cone plate geometry. The Wells Brookfield cone plate rheometer, the CAP 1000 and 2000 viscometers, and the RST cone plate rheometer. The Wells Brookfield rheometer was designed to address the need for small volume sample analysis. Dr. Wells of Mass General Hospital needed a way to test blood viscosity for patients that were prescribed blood thinners. Up until this point, a 500 ml sample volume was needed using standard spindles to measure viscosity. Testing a patient's blood daily over a 1-week period would not be possible, so Don Brookfield Sr. designed the cone plate rheometer. Sample volume was reduced to 0.5 mLs. Today, it is used primarily where sample volume is limited, such as in the medical field and where products have very high cost per ml. The CAP instrument is a high shear rate instrument. It was designed specifically for testing paints, coatings, and inks that are subjected to very high shear rate when being applied. It's possible to test up to 12,000 reciprocal seconds of shear. Using a Peltier plate for temperature control, there is a low temperature version that operates between 5 degrees C and 75 degrees C, and a high temperature version that operates between 50 degrees C and 235 degrees C. The RST CPS rheometer operates both in controlled rate, or RPM, and controlled stress, or torque modes. When you select shear rate mode, the corresponding stress is measured for each given shear rate. When the rheometer applies a controlled stress, the resulting shear rate is measured. Optional software is available for all three instruments, which provides automatic data collection and analysis. As we learned earlier, cone plate geometry is designed to measure materials at known shear rates. The sample is placed between the flat plate and the angled cone. The gap is predefined by the geometry or can be set if flat plate geometry is used. A benefit of cone plate geometry is the small sample volume needed for testing, allowing for rapid temperature control. The Wells Brookfield cones are attached with a threaded coupling. The cap cones are inserted to a holder and tightened with a thumb screw. The RST cones use a quick connect coupling system for easy spindle attachment. There are several cones available for each instrument that provide a wide viscosity test range. You choose the cone that can measure in the viscosity range of your sample. The Wells Brookfield cones are attached to the rheometer using the provided spindle wrench. When cleaning the cone, it must be removed from the instrument to prevent damage to the shaft and bearings. After the cone and cup are cleaned, the cone must be reinstalled and the gap must be reset. This is done without any fluid in the cup. Once the gap has been reset, you can remove the cup and apply your sample to the center of the cup. Sample volume varies between 0.5 ml and 2 ml based on the cone selected. You can verify the accuracy of your instrument by performing a calibration check using a recommended mineral oil viscosity standard and testing at 3 speeds. Again, always remove the cone for cleaning. The cap viscometer cone spindle is attached by inserting it fully up into the sleeve of the instrument and securing it with a thumb screw against the flat portion of the spindle shaft. The sample is placed on the center of the plate using the sample volume specified for the cone spindle selected. When the proper amount of sample is applied, there will be a small bead of sample seen at the edge of the entire cone. If there isn't enough sample applied, you will not see fluid on the complete edge of the cone. If you rotate the cone by hand, you may force the sample to distribute itself over the entire edge of the cone. If too much sample is applied, there will be a large amount of material seen on the edge of the cone and also on the plate away from the edge of the cone. The cap viscometer is the only instrument that can be calibrated by the customer. Using the calibration fluid that corresponds to the spindle and instrument being used, each spindle can be calibrated to the instrument. Using the cone calibration menu, the calibration fluid value, the temperature, and speed are selected. The procedure is then run and takes approximately 15 minutes. Once complete, that cone spindle can now be used on the instrument. Cones can be cleaned in place, but if testing at a high temperature, use caution when cleaning the cone and plate. The cone plate spindle gap, or the distance between the cone and the plate, is very narrow. Particles in some samples can be larger than the gap and can cause inaccurate measurements. The rule of thumb for the maximum particle size that can be tested is 10% of the gap size at the perimeter of the cone. Here you can see the maximum micron size of particles permitted in a sample for each cone. So, to sum up the features and uses for the cone plate geometry, the Wells Brookfield can operate at temperatures between 5 and 80 degrees C. Sample volume is between 0.5 and 2 ml, and viscosity ranges between 0.5 centipoise to almost 8 million centipoise. Applications include blood and plasma, biological fluids, thin coating formulations, precious metal pastes, and gels. The cap viscometer can operate between 5 and 235 degrees C with less than 2 mLs of sample. The viscosity range for the high torque model is 0.2 poise to 10,000 poise. For the low torque model, Viscosity ranges between zero point 0.2 poise to 660 poise. Applications include paints, coatings, inks, resins and polymers, and adhesives. The RST rheometer temperature range is between minus 20 degrees C to 250 degrees C. Sample volume varies from 0.1 to 5 ml. Viscosity ranges from 100 centipoise to 1.6 million centipoise. It is excellent for measuring very thick fluids. It can also perform static yield tests. Applications include pastes, polymers, thick films, inks, and gels. The RST parallel plate geometry can be used to measure static yield at temperatures between minus 20 degrees C up to 250 degrees C. Viscosity ranges from 100 centipoise to almost 10 million centipoise. The gap space between the parallel plates can be adjusted to consider materials with larger particles that can be measured with the standard cone spindle. Next, we'll look at both dynamic and static yield stress. We'll learn about yield stress, the method used for measuring both dynamic and static yield, and which instruments can be used to perform these test methods. So, what is yield stress? It's the amount of stress applied to a material that initiates the onset of flow. As a material is stressed, there is strain placed upon it. At some point, the stress is high enough to cause the material to flow. Strain then drops at this point. Tau zero is the yield stress value at zero shear rate where flow begins. Static yield applications include foods such as yogurt, mayonnaise, and peanut butter, cosmetics like lipstick and mascara, personal care products like creams, body washes, and toothpaste, and pharmaceutical gels and hand-applied products like adhesives, sealants, and lubricants. Dynamic yield applications include screen printing inks, dip coatings, and enrobing or slumping materials. How do we determine yield stress? First, let's look at dynamic yield stress. Dynamic yield stress can be measured using standard viscometers with coaxial cylinders or cone plate geometry that allow for measurement of shear stress at varying shear rates. Static yield can be measured using a stress ramp on a control stress rheometer or a constant rate test using a vane-based rheometer. Static yield stress is typically higher than dynamic yield stress. Dynamic yield stress can be used for materials that are flowing at some point and then stop flowing. Examples are screen printing inks, dip coatings, and chocolate enrobing. Static yield is more appropriate for materials that are stationary before use and require a stress to begin movement. This includes products like peanut butter, ketchup, mayonnaise, and materials that must be mixed or pumped in order to get them moving. Using the DV3T or DV-Next rheometer with the small sample adapter accessory allows for the calculation of dynamic yield stress using the math models available in the instrument. If you use a DV2T with optional RheoCalc software, you can use the math models in the software to calculate the dynamic yield. As previously mentioned, dynamic yield is best suited for materials that will be flowing at some point before application or for materials that undergo start and stop flow. The test method for dynamic yield stress requires generating a flow curve of shear stress versus shear rate. Plotting the data using a best fit line, you extrapolate to the y-axis of shear stress to determine the value at zero shear or tau zero. Measuring static yield stress requires a control stress rheometer. You can use either a cone spindle with a cone plate rheometer, a coaxial cylinder spindle with a coaxial cylinder rheometer, or a vane with a soft solids tester rheometer. The applications are typically for materials at rest that will need some stress to initiate flow, such as gels, pastes, creams, and slurries. For determining static yield stress, a control stress ramp is run where the stress level is steadily increased with time. At some point, the stress will be high enough to initiate flow of the sample. This is the static yield stress value. As you can see in the top graph, the initial shear stress is very low and there is no shear rate or spindle rotation noted. At some point along the control stress ramp, the shear stress level is high enough to initiate product flow. This is called static yield stress. The lower right graph compares two conditioners with measurably different static yield stresses. Here's a close-up view of the control stress map. A cone plate rheometer was used with a 75 millimeter cone. The stress ramp range was from 0 to 160 pascals over an 80-second period. Product number 2 begins flowing at 20 pascals of stress, while product number 1 begins flowing at over 100 pascals of stress. Perhaps the size of the container outlet is smaller for the first product and larger for the second product. The second method for measuring static yield stress is to perform a constant rate test. This can be done using the DV-Next rheometer and a vane spindle. The vane is gently lowered into the sample with minimal disruption, and a very low speed is run. The DV-Next has a custom algorithm that determines the yield stress and apparent yield strain. This test can be run in standalone mode or with rheocalc software. The recommended speed for this test is 0.5 RPM. The drive motor applies a constant rate to the clock spring while the center of the spring is attached to the stationary vane spindle in the sample. As time passes, the strain on the spring increases linearly with time. An algorithm predicts this strain versus time relationship, as can be seen by the dotted line in the graph. Eventually, the strain on the spring and vane is high enough to cause the vane to initiate flow of the sample. At this point, the stress on the spring is slightly relieved, and the algorithm then reports the maximum stress recorded prior to the initiation of flow. This stress value is reported as the static yield stress. I hope this training module has helped you gain an understanding of the three types of cone plate instruments, their geometries, operation, and applications. If you have any questions regarding this training module, call 508-946-6200 or visit brookfieldengineering.com. We will gladly answer any questions you may have.